Hello students and welcome to my channel Maths Hub. So in this video series of partial differential equations, today we will be studying about the Lagrange's linear equation, right? So what is this Lagrange's linear equation all about? So a standard Lagrange's linear equation will be of the type PP plus QQ is equal to R, where capital P, capital Q and capital R, they are all functions of X, Y and Z, right? And in the previous video, I've already explained that what are small p and small q. Small p is del z by del x and small q is del z by del y. So what are the methods to solve any Lagrange's linear equation? We will first find out the Lagrange's auxiliary equations, which are represented by dx by p is equal to dy by q is equal to dz by r. Then we will try to solve any two of these equations and we will get two different solutions. And by combining them in this form, suppose u equal to a and v equal to b are the two different solutions of these auxiliary equations. We will combine the two solutions in this way and that will give us the general solution of the given PD, right? So let us try to use this concept in certain exercises. So in this topic, the more you practice, the more exercises you will be able to solve, right? So we will move from very simple problems to complex problems. So let us solve the first differential equation. So we are given yq minus xp is equal to z. So the first thing that we need to do is that we will compare this equation with pp plus qq is equal to r, right? So when you compare this equation with this, we will easily get that capital P is minus x, capital Q is y, and r is equal to z, right? So let us frame the Lagrange's auxiliary equations. And when we get the Lagrange's auxiliary equations, we get dx upon p, that is minus x, dy upon y, dz upon z. Now, since it's very simple, you can see that if I take these equations, dx by minus x and dy by a, dy by y, I can simply integrate these equations and I'll get minus log x is equal to log y plus log any constant, right? So you can put any arbitrary constant here, right? Then we can take log y to this side. Both will have a negative sign, so that negative sign can be transferred onto the constant. And we will finally get log x plus log y is equal to log c1, right? And when you remove the properties of log, you will get xy is equal to some constant c. So I need to get two different solutions. So this is my first solution. Similarly, we can solve these two equations. Dy upon y is equal to dz upon z. And when you solve these two equations, you can simply integrate them and we get log y is equal to log z plus log c2. And similarly, I can take this log term to the left side. It will become log y minus log z. And that will turn out to be log y by z is equal to log c2. And hence, on removing log, we will get y by z is equal to c. Right? Then finally, how to combine the solutions? We will write the function f. We will write the first solution, that is x into y. We'll write the second solution, that is y by z. We'll remove the constants and we'll put it equal to 0. So this becomes the solution of the given PD, right? So I'm again repeating the steps. You have to frame the auxiliary equation. After framing the auxiliary equations, we have to take two equations at a time. We need to make it integrable, and then after solving it, we will get two different solutions, and by putting the solutions in this form, we will get the final solution of the given case, right? Okay. So now let us try to solve another problem. As I told you, the complexity of the problem will increase with every question. So see, solve y square p minus x into yq is equal to x into z minus 2y. So you need to identify first of all p, q and r from the given problem. So you can easily see that p is y square, q is equal to minus xy and r is equal to x into z minus 2y, right? So let us try to frame the auxiliary equations. So we get dx upon y square is equal to dy upon minus xy, that is equal to dz upon x into z minus 2y. So very easily you can see that you can take up the first two equations. So when you take up the first two equations, dx upon y square is equal to dy upon minus xy. So y gets cancelled and you can cross multiply the terms. So we will get minus x dx is equal to, or you can take this minus sign on the right hand side. You can leave it on the right hand side, is equal to y dy. And now you can see it is easily integrable. So x square by 2 is equal to minus y square by 2 plus constant c1, right? And finally we get x square plus y square is equal to 2c1. So this is one of my solutions. Let us try to find out the second solution. Now which two other equations we can take? We can take dy by minus xy is equal to dz upon x into z minus 2y, right? So you can cancel out x on both sides, and now as you can see that this term is containing both z and y. So what can be done? We can just cross multiply the terms and we will get z dy minus 2y dy is equal to minus y dz, right? So out of all these terms, you can see that only this term is integrable. It is only containing y. So let's take this term on the right hand side. So we get z dy plus y dz is equal to 2y dy. Now this is integrable. Can we make this integrable? Now what is z dy plus y dz? Isn't a total derivative of the product y into z? If you open up this, you will get y and z are both independent variables. So y constant derivative of z is dz, z constant derivative of y is dy. This is equal to 2y dy. And when you integrate it, what will you get? Yz is equal to 2y square by 2. So 2 will get cancelled. Y square by plus c2. So we get yz minus y square is equal to c, right? So what is the final answer then? We will put these two solutions together. So we have x square plus y square, comma, yz minus y square. This is equal to 0, right? Okay. So now let's move on to the next question if you've understood it. So the next question says, solve x square minus yz into p plus y square minus zx into q is equal to z square minus xy, right? So identify your p, q and r. So p is x square minus yz, q is y square minus zx, and r is z square minus xy, right? Now, from all these variables, let us try to calculate the auxiliary equations. So the auxiliary equations are dx upon x square minus yz equal to dy upon y square minus zx is equal to dz upon z square minus xy, right? Now, from these auxiliary equations, let us see how to solve them. You can see that if you take two terms at a time, you won't be able to solve it because they are not integrable, right? So how to make it integrable? Now you can just assume these equations to be in the form of a ratio. So if I assume that this is a ratio, so let it be A by B is equal to C by B is equal to E by F. So I can apply all the properties of ratios. I can say that this ratio is also equal to A minus C upon B minus D. Its ratio is also equal to C minus E upon D minus F, right? And it is also equal to A minus E upon B minus F. Now, why are these ratios equal? Because if they are ratios, they will be equal to some constant K. So if I take this expression, I can just put in the values of A and C. So if I compare A by B equal to A, so A comes out to be K times B. Similarly, if I assume C by D is equal to K, C will come out to be K times D. So if I substitute these values here, it will become KB minus KD upon B minus D. So K will come out and we have B minus D upon B minus D. So B minus D cancels out and the ratio is also equal to K. And likewise, you'll get the same thing, right? So we will try to apply this concept here, right? So how is this concept applied here? Let's see. Now, whatever we do, we have to make it integrable, right? So we can add, we can subtract, we can add all the terms together, right? So how it is done? Let us see. Let us calculate dx minus dy, dy minus dz, and dz minus dx. So when I subtract the numerators, I have also subtract the denominators. So I will get x squared minus yz minus y squared plus zx. Then y squared minus zx minus z squared plus xy. And then dz minus dx would be z squared minus xy minus x squared plus yz. Now let's combine x square and y square and yz and zx. So when you combine x square and y square, we will get x square minus y square. And from these two terms, I can take out z common and I will get x minus y. So x minus y is common. What is left inside? We will get x plus y plus z. So this is what is the term we are getting here, right? Similarly, dy minus dz, so I can combine y square and z square and zx and xy. So when we combine and make factors, we will get x plus y plus z into y minus z. Similarly, dz minus dx, we can take out factors. We will get x plus y plus z and z minus x, right? So all these ratios are equal to each other. Now, let us, so from all these ratios, you can see that x plus y plus z is the common factor. It gets removed. So we get dx minus dy upon x minus y is dy minus dz upon y minus z is equal to dz minus dx upon z minus x, right? Now let us take two of these equations at a time and solve them. So when I take these two equations, dx minus dy upon x minus y is equal to dy minus dz upon y minus z. Are they integrable? Are these equations integrable? So let us see. Let us put x minus y equal to t. So when we take the derivative, we will get dx minus dy is equal to dt. So this becomes dt by t, and similarly if I put this equal to u, I will get u du by u. So they are integrable. So we will get log t is equal to log u plus log c1. So from here log t minus log u, simply I will get t by u is equal to c1. So when I substitute t, it is x minus y, and that is y minus z is equal to c. Similarly, we can take these two equations, and when we take these two equations, we will get a similar thing. Dy minus dz upon y minus z is equal to dz minus dx upon x minus z minus x, right? So again, you will see that this is log of y minus z is equal to log of z minus x plus log c2. So I can combine them and I will get the equation y minus z upon z minus x is equal to c. And when finally, what is the solution? The solution would be x minus y upon y minus z. And from here, we will get y minus z upon z minus x is equal to 0. Right? So this is how we will find the solution for this particular linear differential equation. Okay. So now let us try to solve another question. So in every question, the concept of calculating the integrating the concept, the equations are different, right? So the more you practice, the more it will become clear. So there is one more concept. So if these are the auxiliary equations, it might happen that sometimes we might have to multiply with a constant, the numerator and denominator with the same constant, and we add them. So dx by p is equal to dy by q is equal to dz by r. and we can multiply them with L, M and N. So it will become L dx plus M dy plus N dz upon LP plus MQ plus NR, right? So what is the use, how to choose these LMN? We can choose these LMN in such a way that the denominator terms become equal to 0. So if the denominator terms becomes 0, if this is 0, so I can put it equal to some constant. And when I put it equal to some constant, I will get the simple equation as L dx plus M dy plus N dz is equal to 0, right? So let us try to use this concept in this exercise. So we have to find out the general solution for this differential equation. So first of all, we frame the auxiliary equations as dx upon x into z square minus y square, dy upon y into x square minus z square, dz upon z into y square minus x square, right? Now we can clearly see that if I multiply this equation with x in the numerator as well as in the denominator, multiply this equation with y in the numerator and denominator, and multiply this equation with z in the numerator and denominator, and add up all these equations, what will happen? Let's see. We have x dx plus y dy plus z dz, and denominator terms we will get is x square, I'm opening up the brackets also, x square y square plus y square x square minus y square z square plus z square y square minus z square x square, right? So you can see that this term gets cancelled with this gets cancelled. So the entire denominator is becoming 0. So x dx plus y dy plus z dz is equal to, so if I put it equal to some constant k, I'll get this equal to 0. And when we simply integrate it, we will get x square by 2 plus y square by 2 plus z square by 2 is equal to constant c1. So x square plus y square plus z square is equal to 2c1, right? So this is one of your solutions. What is the second solution? Now, instead of multiplying with x, can we multiply with first term with, if I remove this x, that means if I multiply with 1 by x, 1 by y and 1 by z, still will the terms get cancelled? Let us see. 1 by x dx plus 1 by y dy plus 1 by z dz upon. When I multiply the first term with 1 by x and x cancels, we are left with z square minus y square plus we are multiplying the second term with 1 by y, so we will get x square minus z square. And when we multiply the third term with 1 by z, we will get y square minus x square. So can we again see the terms are getting cancelled, right? So if I put this equal to some constant k, I will get 1 by x dx plus 1 by y dy plus 1 by z dz equal to 0. So you can easily integrate it, right? And when we integrate it, we will get log of x plus log of y plus log of z is equal to log c2, right? So you can combine them, x, y, z will become equal to c, right? So what is your final answer? The final answer will become f of x square plus y square plus z square, and x, y, z is equal to, clear? So these multipliers are very important. So you have to choose the multipliers in such a way that the terms get cancelled or they become integrable, right? Okay. So I'll give you one more question. To solve these questions, try this. The answer is already given in the presentation in this video. So do not check the answer before you attempt it. Do it first and then check the solution, right? And then after doing this exercise, you can try these questions So try these questions and do let me know if there is any doubt in any of these questions in the comment section, right? So thank you so much for listening to me. And if you like the video, do hit the like button. And those of you who haven't subscribed my channel, do subscribe my channel to get the latest updated video. Thank you so much.